All right, this is 7.3b, and we are going to do, it's pretty similar to a two-sample z-test for average, for mean. The problem is the z distribution, the normal curve, requires that we know the population standard deviation. And they briefly touched on this in the Zybook, but not very much. So if you are going to use a z-score and you're going to shade the normal curve. So the normal curve looks like this. And we we have a sample average, and then we have a, sorry. We have a population average, and then we have a sample average, and then we shade over here, and then we accept or reject the null. Okay. Did we do t-tests with one sample? We had to have. So the problem with doing this with sample average is we don't know the standard deviation of the population. And as we have developed statistics, we've realized that the number of people in the sample is going to affect the accuracy of our calculation of a z-test. So we have to use what's called a t-test. And the t-test is really similar to a z-test. It has a curve that's not quite normal. It's squished a little bit from normal. It's still symmetric on both sides. And the difference is every curve depends on how many people are in the sample. So we get a series of curves that just look like this. And every curve is tied to the number of people in the sample. And eventually, if we talk to enough people, then the standard normal curve and the t-curve are indistinguishable from each other. Okay, but we're not going to get too much into that right now. So the nice thing is the computer is going to do all the work for us. So in old statistics, like the way I learned it, you didn't have a curve. You actually had a table of values, and you would look up the number of people in your sample, and then it would give you some values, and you would just compare it to that. We're just going to use the Rossmann one chance, and it's going to spit out all the answers for us. So just know that every single one of these curves is based off of a different line on the t-table, according to how many people are in the sample. Okay, and it's a little bit different than a normal curve, but as long as your sample is large, it's not a very big difference. So the first question asks, maybe, hypothesis test for two sample means require we use the t-score instead of the z-scores. Why is that? The answer is we don't know the population standard deviation. And if you don't know the population standard deviation, you cannot use the normal curve. You have to sort of squish your curve according, and the amount that you have to squish it depends on how many people are in your sample. So when we do these, you're going to see t values instead of z values, and that's the reason. When we did proportion, it wasn't a big deal because our standard deviation was based off of the number, the percentage of the sample, and it turns out that that's accurate enough that we don't need to worry about t-tables. Okay. So for each of the following experiments, state the null and alternative hypotheses, and then use the Rossmann one-chance theory app to calculate the difference for the sample means, the standard error of the difference between means, the number of tails, the t-score, and so on. All right, so two teaching methods are implemented at a school in different classrooms. All students are given a test at the end, and the two methods are compared to each other. Method A, what is this? I don't know. Method A was given to 135 students, and the average test score for that group was 85, a standard deviation of 7. Method B was given to 128 students, and the average test score for that group was 82, a standard deviation of 6. is there evidence to suggest that method A is better than method B? So, one or two-tailed test? One, why? Is A better than B? So that's going to be one-tailed. So, our null hypothesis states that mu for A is equal to mu for B. Oh no, that's not how we do it. I mean, that's really what we're testing, but we don't write it that way. We're going to say minus mu of B is equal to 0. And the alternative hypothesis, mu of A minus mu of B is greater than 0. Okay. What is the difference between the two samples? 3 percentage points. And remember, it's not 3%, right? The difference between them is going to be a lot bigger than 3%, but it's 3 percentage points. All right, so let's pop up our Rossmann. And then you want to go to theory-based inference. And we want to do two means. And our first sample is 135. And our second sample is 128. And 0.85. And 0.82. And standard deviations are going to be 7, or 0.7, sorry, 0.07. And 0.08. Actually, you know what? I didn't even need to do, we could have just done 85, 82, but this will still work. And then 0.06. Does that make sense? Whether you display this in a percentage or a decimal is not going to make any difference. You're going to get the same results. So calculate. We want a test of significance. And we want to change it like that. And calculate. All right, so my t statistic is 3.74. So on the last worksheet, the rule of 1.64 and 1.96, that doesn't actually apply here because those are for z-score tables. Now, we kind of cheated yesterday and we assumed that we were doing a z-test when we really weren't. So if you get 1.8, you may or may not reject the null depending on how many items are in the sample. Okay, but obviously 3.74 is off the chart. The p-value is 0.0001. So number 7, is there evidence to suggest that method A is better than method B? What are you going to answer? Yes, and what's your explanation? We rejected the null and accepted the alternative, which means there is a significant difference between, or A is significantly better than B. And make sure when you do these explanations, you use the word significant. That's sort of our magic word in statistics. So we say A is significantly larger than B. Okay, think you can handle that? Yeah? All right. Get to work, and then tell me all my mistakes. Uh-oh.